Hello everyone. In this problem we are required to verify first a particular homogeneous solution to this ordinary differential equation and then find the general solution. Concerning the differential equation itself, it's second order due to the second derivative, linear since it's a combination of the variable x and a few of its derivatives. Non-homogeneous, we have a non-homogeneous term on the right, and variable coefficients Well, the first part is easy. Verify is always nice. Doesn't mean solve. Do not solve. It's just calculate all derivatives, plug them in, check if the differential equation holds. So if x of t equals 1 over t squared, which is t to the negative 2, I rewrite it as a power in order to facilitate the calculation of the derivatives. X prime ends up being negative 2 times t to the negative 3 power rule, and x double prime would be 6 times t to the negative 4. So substitute in the differential equation, so t squared times x double prime, which is 6 over t to the power of 4, plus 3 times t, x prime, which is negative 2 times over t cubed, equals, and important, we were told that 1 over t squared would be a particular homogeneous solution, so it must be a particular solution to the associated homogeneous differential equation. If it's second order, we expect two linearly independent homogeneous solutions, one of them being 1 over t squared. Well, if we simplify, t squared, t to the power of 4, t cubed ends up being t squared, so at the end of the day it's just 6 t squared minus 6 over t squared equals 0, and therefore verified. Okay, verified. Now that was easy. The tough part would be to find the general solution, including the non-homogeneous part. Well, it's non-homogeneous, which is already bad. Moreover, the coefficients on the left are not constant. They are varying. They are functions, to make it even worse. So what do? Should we run away and hide? Should we shake our heads in despair? Well, not quite, since, well, we know that when everything is changing, non-homogeneous variable coefficients, there is a way to find the solution, but it takes a lot of time. So in math, it's important to be smart, be efficient, and consider the differential equation, look for patterns. It's true, I will rewrite it. So t squared x double prime plus 3t x prime equals 1 over t. It's true that it's second order linear non-homogeneous variable coefficients, but it's also reducible to a first order, since we have in the differential equation it's a function of the input t in this case, output prime, and output double prime equals 0. Okay, it's a function that does not include the output itself. In those cases, there is a nice substitution. You can check your notes or the cheat sheet. There is a nice substitution to simplify tremendously the structure. That substitution is the following: x prime equals u, hence x double prime equals u prime. So the differential equation transforms to t squared u prime plus 3t u equals 1 over t. Divide everywhere by t squared. So u prime plus 3 over t u equals 1 over t cubed. I'm doing this to have a 1 as the leading coefficient, and this is one of the basic structures. It's linear first order, linear first ordinary differential equation. In this linear structure, 3 over t is what we call p of t, and the right hand side of the equation q of t, the non-homogeneous part of the linear structure. So the solution involves the calculation of an integrating factor. So integrating factor, whenever we find one of the so-called basic structures, separable, linear, exact, we feel comfortable. There shouldn't be too many surprises in there. So the integral of p of t dt, it's the integral of 3 over t dt, which is 3 times natural log of t. Do we need to include the additive constant? Remember, there's only one case in differential equations in which it's safe to assume the differential equation is the additive constant is 0, and that case is when calculating an integrating factor. So let's assume it's 0. It will not affect, by definition, the result. So the integrating factor I of t equals exponential of 3 natural log of t, and using log rules, this is exponential of natural log of t cubed. Exponential and natural log, they cancel out, so the integrating factor is t cubed. Final step, we know that in linear structures the integrating factor times the linear variable equals the integral of integrating factor times q of t in this case. Therefore, it's integrating factor times linear variable equals the integral of integrating factor times q. Very nice q, by the way. Everything cancels on the right, almost as if it was rigged, almost as if the person who set up the problem was a nice person. I'm joking. Integral of 1 with respect to t is just t plus additive constant. Please do not forget the additive constant when solving an integral. Only we can neglect it when calculating the integrating factor. So divide by t cubed left and right, so u equals 1 over t squared plus constant over t cubed. Looks nice. Is that the end of the problem? Not quite, since u means nothing. U was just a substitution tool to help us solve the problem. So we need to substitute back, knowing that u equals x prime, and therefore x should be the integral of 1 over t squared plus c over t cubed, everything with respect to t. So integral, let me rewrite it using power properties so that it looks like a integral of a power, much nicer. Integral of t to the negative 2 plus constant times t to the negative 3, differential of t, so this is minus 1 over t plus constant times t to the negative 2 divided negative 2 plus another constant, and cleaning up, reabsorbing the constants. This is minus 1 over t plus constant divided t squared plus constant. And yeah, I know that I'm using the same symbol. If you don't feel comfortable with it, I'm talking about c. You can rename it, but it's still a blind constant. So I'm assuming that in case of doubt, that c over negative 2 in here is just an unknown constant c. So there you go. Solution. Oh, solution to the general solution to the differential equation.